Okay, let's start this. So we're going to be talking about log-free programming, and well, we'll see what place it occupies. At least I think it should occupy in modern programming. The talk will have three main acts with the introduction, and there will be a big surprise at the end. By way of doing at least one impossible thing, I wanted to try to summarize the whole talk on one slide. And here is that slide, and if you can't read it, do not worry, everything will be revealed toward the end. So, the technical details, but why now? I gave this talk in 2017 at CPPCon, this is the title slide, and the message was something that was considered basically common wisdom at the time. It was an educational talk. I wasn't breaking any new ground, I was explaining what everybody knew at the time. Log-free code is hard to write, you concentrate it in the critical places, you encapsulate it, you do the most demanding things log-free if you have to, and usually that means places of the highest contention. So almost 10 years after that, all of the machinery is the same, all the tools are the same. Yeah, cplusplus added a few things, but nothing like fundamentally radically new. And me and everybody else appears to be almost 100% wrong. So let's see what changed and what can we do. Okay, let's talk about log-free programming versus log-based programming. So these are the classical definitions. There is the wait-free, where every thread always makes progress, no waiting, no loops. Fetch add is an example of that. There is a log-free, where multiple trees attempt to make progress, at least one succeeds. Losers just retry, but somebody makes progress, so the program overall is always advancing toward its goal. Compare exchange is the common tool in that style. And the last one is the log-based. One thread holds the log, everybody else waits. At most, one thread can make progress. Even that is not guaranteed, because the thread that is holding the log could be otherwise preempted from progressing or could decide not to progress. That's the log-based stuff. Okay, is log-free faster than log-based? Well, it seems like it should be, because in a log-based program, at most one thread is making progress, it's the slowest. So, since we're interested in the highest contention scenario, we're going to benchmark and we also want to compare wait-free with log-free, which limits our choices. We're going to benchmark an increment of an integer in this case. The reason I've chosen that is because it's one of the few things where you can actually compare wait-free and log-free. Typically, it doesn't make sense to compare wait-free and log-free, but since we want to have this full benchmark, fetch add is wait-free, but you can write compare and swap loop instead. There is no reason for you to do it in real life, but for benchmarking, why not? And actually, as it turns out, there is a reason for you to do it in real life. Okay, here it is. That's an x86 Intel machine. Throughput, number of increments, increment time, inverse of throughput. Average increment time. Average increment time, inverse of throughput in nanoseconds. Number of threads, this machine can go up to 96, I think. So the bottom line is the spinlock. We'll see how spinlock is actually written, but it's basically a mutex just implemented differently. Here is the fetch add. Here is the cas. On an x86, it makes no difference whether it's weak or strong. I was just generating all the charts with weak cas, so they all say weak. And here is std mutex. Okay, other than std mutex is an inefficient mutex, at least for this sort of workloads, log-free, even wait-free, isn't actually doing so hot. Okay, does it depend on hardware? Here is the Apple M3 Pro core, 24 core machine. The amazing thing on this one is actually this region over here. This is std mutex. Std mutex at large number of threads actually beats fetch add. Now that's more of a credit to whoever wrote that std mutex than anything else, because the spinlock is still way faster. Okay, is that the x86 versus the ARM thing? No, it's not. Here is the Grace part of the Grace Hopper, NVIDIA ARM-based chip. It basically looks very similar to the Intel. There is a little bit less, less difference between spinlock and weight-free, but still the same. Graviton looks which is another ARM-based chip, looks very similar to this. So no, it's not an ARM thing. Okay, so under high contention, spinlocks appear to outperform atomics, and lock-free in CAS is slower than weight-free, but this is typically a false choice. You normally can't do weight-free, and if you can, just do it. There are different kinds of locks, obviously, but the other thing that you should notice on this, well, none of this actually scales. Everybody gets slower with the number of threads. So not even the weight-free ones scale, but the weight-free, the definition is all threads make progress at all times. If all threads make progress at all times, how come it doesn't scale? Okay, let's talk about the weight-free. It's a big lie in the definition. It's actually a kind of, it's CS definition. It refers to algorithmic steps. It doesn't refer to clock ticks. At the high level algorithmic steps, yes, everybody advances. At the hardware level, at the clock cycle level, there is still exclusion. There's locks at the hardware level. Only one thing is happening at a time. At the hardware, otherwise you would have data races. And benchmarks clearly show that atomic increments, single atomic instruction, become slower under contention. So why? Well, we need to talk about the cost of data sharing. The working hypothesis is that it's the access to the cache line. Getting exclusive access to the cache line is what's expensive. How do we prove it? We want to separate access to the cache line from actually access to the shared data. There is a clever hardware hack that exploits the idea that cache lines are bigger than the data some of the data you can operate on. In particular, most cache lines are 64 bytes. On most systems, you can do atomic ints, which is only 4 bytes. So let's not share any data. Put multiple ints on the same cache line. There is no sharing, but we do want exclusive access to that entire cache line. So let's find out if doing that would make our increments slower, faster or not. We get rid of data sharing. We don't get rid of cache line sharing. Let's split these two components and find out. So this is basically what the test we're going to do. Since the cache line gets locked for exclusive access at the line granularity, we can see if not sharing data but sharing cache lines is what kills our performance. You do it like this. Here is your true sharing. Everybody hammers this atomic variable. Here is your false sharing. You have an array and you hit adjacent elements of that array. As long as you have not too many threads, you will be hitting the same cache line. As you have more threads, obviously you will run out of integers you can stuff into the same cache line, and you'll start hitting 2 or 3 cache lines. And then if you basically if you separate your indices far enough, so you would have to choose non-contiguous indices, then there would be no sharing.
I didn't understand that last line.
The last line, sorry.
The one above it. Pseudoatomic int is new int array. It looks like the new type and the type of the variable are different.
Yeah.
Should it be new pseudoatomic?
Yeah, it's a new pseudoatomic, sorry.
But that doesn't go this way.
Okay, yeah, it's a new pseudoatomic of int.
Correct.
Okay, and
even so, it's an array of those, say, sit next to each other.
Exactly.
And
how do you separate?
like
When you
that.
will have lots of news.
Yeah, you can do lots of news. You can stagger it. So you can do lots of news. You're relying on malloc to not produce adjacent things. Typically, it doesn't. Okay, but now I lost my cursor.
Why 8?
should be.
Oh, did I say int? I said int, not long. Okay, it's 16 for ints. For longs, it's 8. Sorry, I said ints. Okay. Okay, so not sharing cases is trivial. You get perfect scaling if you get the index right. It's the false sharing case that we're interested in. So here is the true sharing where we're hitting the same atomic, and here is the false sharing. It starts off exactly the same. Then it kind of goes in between. But it starts off exactly the same. So for small number of threads, it doesn't matter if you are actually incrementing the same int or just ints on the same cache line, same cost. So why is it happening this way? Well, the modifying any data on that cache line requires exclusive access to that cache line. Doesn't matter how much of the data you modify, and wait free isn't constant time. It's constant number of instructions, but not constant time. Instructions themselves take longer. Yeah.
So the last spinlock, was it x86 or
Yeah, that was x86.
was it like SMT or non-SMT?
For the small number of threads, they're pinned onto physical cores. When you can extend it into SMT range. It's a big enough machine that it can do like 64 threads without hitting SMT.
So if the SMT is like SMT another system, then it makes sense, right? Two thread if they both thread.
If you allow them to go on the SMT sibling, then yes. But no, they're scattered on the physical cores first when you run out of physical cores. Yes, on SMT machine there is what's called SMT sibling, which is the one, there is one core, out of all your cores, there is one other that actually shares the L1 cache with you. Okay, so basically, what we learn from this is, okay, modifying shared data requires cache locking, and that's where the main cost comes in. And even in wait free, even though it says all threads are making progress, well, they're executing the instruction, but only one of these instructions can be modifying the shared data at any given time. So in hardware, they'll just have to wait. The instruction count, all threads are executing instructions. Only one of those instructions will be doing work, everybody else will be blocked, and that happens at the hardware level. Now, read-only access is the exception. It does not require cache locking if everybody does read-only access. So there is a niche for lock-free programming that exploits that advantage. We won't be talking about that. Okay, so what we've seen, and now we're done with the introduction. We arrived to Act 1, where the locks get introduced. We've seen that locks work better at high contention than the alternatives, at least some locks. So let's see what those some locks look like. Okay, so this is the spin lock. This is the spin lock that I was using at high level. I'll give you some details. Okay, so there are several details here. First of all, they're all based on some kind of atomic, and I've chosen atomic of it. And it doesn't matter, the values that you'll be playing with are 0 and 1. 0 is not locked, 1 is locked. To lock it, the right way to lock it, and you'll see why in a moment, is first to probe it with a read-only access. If you got back 0, it means you have a chance. If you get back 1, you just bail out. Okay, not gonna lock it. This time, try again. But if you get back 0, now we actually have to lock it. Of course, it could have changed in the meantime. The way you actually lock it is with atomic exchange. Read, modify, write. You don't need compare and swap for this. You just do atomic exchange. It unconditionally replaces whatever there was with 1, which could have been 1. So you could replace 1 with 1. It counts as replacement. In hardware, it counts as a write. It doesn't matter that the bits were the same. You get back whatever was there. If you got back 1, you replaced 1 with 1, which means you didn't get it. If you got back 0, you got it. Okay, so this read is first critical part of making good locks. The second critical part of making good locks is actually if you can't get it for a while, you have to yield the scheduler. There are multiple different ways to yield the scheduler. I'll show you the one that experimentally I found to be the best, at least on the Linux systems. Yeah. Okay, unlock is very simple. You always store 0 unconditionally and give up the lock. Unlock is actually the hard part of that. It looks simple. All right, why pre-read? What happens if you don't pre-read? Well, in order to modify if you don't pre-read, you will immediately do exchange. Exchange is read, modify, write. A write portion of it requires exclusive access to the cache line. If one core has exclusive, everybody else has that cache line marked as invalid. So if you're hitting it with atomic exchange, any core that tries to acquire a lock invalidates that cache line on all other cores, whether it acquired successfully or not. You don't want that. You don't want the cores which are failing to acquire a lock to steal the cache line from the ones that actually do hold it, because then they would have to get it back.
Quick question.
Yeah.
How do you validate that behavior? Is that just your understanding of the architecture?
You benchmark with like with reads, without reads, different number of pre-reads, how many times to pre-read.
Okay.
You benchmark that. Okay. So now, how does that invalidation actually work? Invalidation works, and that part you just from the documentation of these CPU architectures. The way the writer gets exclusive access to the cache line on modern CPU is what's called the read for ownership. You actually do a read first, but it's a special read that gives you exclusive access, RFO, read for ownership. The problem with that is you have to wait for all the other cores to send you back the acknowledgement. They respond actually with an ACK signal that they invalidated their cache lines. That takes time. The reason it takes time is actually because of the speed of light on modern GPUs. Takes a while to communicate from one end of the chip to the other. They're big. Turns out that they're big enough that it matters. Now, if you do put read in, then you can read the lock variable while remaining in a shared state. You don't have exclusive state. And that immediately gives you advantage over atomics, where fetch, add, or cast, which are both modifying instructions. You can't probe a cache line without getting it exclusive if you're doing lock-free, but you can if you're doing lock. Okay, now you have the read. Readers are happy with just the S state shared. That solves your lock acquisition problem. You now don't pull the cache line from whoever is acquiring them. But now you have another hidden problem that actually much fewer people talk about, at least from what I've seen, and that is unlocking the lock. To unlock, you just unconditionally write 0. The problem is, if somebody else tried to acquire it while you were holding it, they got shared state on that cache line. You were exclusive. Okay, show you the protocol. So everybody was in a shared state. You succeeded on exchange. You wrote, you got back 0. You're holding the lock. Okay, so you're unmodified. Everybody else is invalid. Somebody else comes in and decides to acquire that lock with a pre-read. They're being good. They're being as good of it as they can be. They get shared, not exclusive, because they're doing a pre-read. They drop your modified into shared. Now you want to unlock it. You need to modify it again. You need exclusive access to unlock, which means to unlock it, you have to issue a second RFO. Unlocks, even though they're unconditional, very simple, they're actually slow, because there is a second RFO there. Unless, of course, all the threads that failed that would have been trying to acquire the lock were asleep at this time and weren't hammering you with the reads. In which case, your odds are pretty good that you're still holding it and modified. And the way it actually scales with how many of these acknowledgements you need to receive. So two parts of this lock. Pre-read avoids bouncing the modified state across the cache lines. Aggressive backoff, going to sleep if you fail to acquire it, keeps you from stealing the cache line from the only thread that can actually unlock it. You want unlocks to be fast because that's the only way anybody else can make progress. It turns out you can prevent other threads from unlocking by constantly stealing their cache line by reading it. Well, backoff is what solves that problem. So now, with backoff, at high contention, you have fewer threads trying to read it. Fewer threads would need to send their acknowledgements to the RFO. It gets faster. So two things, pre-read, and actually to get a good spin lock, it's not enough to do one pre-read. You need to do multiple pre-reads. Why? Because a read is a lot faster than RFO propagation. Like on x86, you can do about 8 reads. It takes, in time, it takes for you to receive your RFO back. So even if you're, let's say you were the thread that was destined to get the lock. But if you don't wait long enough, you will give up before the acknowledgements come in. So 8 reads is what I do, empirical number. Turns out it's not very critical. 8, 12, like 4 is not enough. 16 starts to drop off a little bit, but you have to experiment. Apple Silicon uses a different protocol. It trades power efficiency for latency, so atomics are actually even slower on Apple Silicon because instead of very fast and very power-hungry cache coherency machinery that x86 and Grace and Graviton use, they put this kind of multi-level hierarchical directory is very power efficient, very long latency. So interconnect on Apple Silicon has longer latencies. That's why atomics lose so badly to the locks. There is actually a way to rescue cache loops on Apple. I'll show you if I have time. Okay, fine. Locks give us better performance at high contention. Why don't we use locks if things are that good? Well, okay, there are several reasons. There are all these problems with locks. You can deadlock, there are live locks, there is preemption. That one will be important for the rest of the talk. Preemption means a thread that is holding the lock is delayed for some reason, and now nobody can proceed. If you write lock-free code, that cannot happen to you. Of course, at the cost of basically doing this, where you could have been doing this, but spinlock can be preempted, CAS cannot. There are some other problems. There is a starvation where the thread that releases the lock is in a preferable position to acquire it unless you assure fairness somehow, starves everybody else. There is convoying, it's an artificial contention that happens after random delays. None of this can happen in lock-free code, but the cost is significant. Okay, so locks can work better than atomics at high contention, but actually it turns out that locks can work even better. We can avoid some of the problems with locks if we change the way we use our locks. So that's point number 2. So point number 1, at high contention, locks on equivalent sort of workload, locks on modern hardware outperform atomics. Point number 2, there are actually good ways to use locks. So there is log-based, there is log-free, there is something else. Okay, and to do that, let's look at the atomic maximum to figure out what something else is. So here is your thread-safe maximum. We can do it with a lock. Very simple. Here is my nmax. I take a log. Here is my current value. If it's greater than nmax, I update nmax. Yeah? Yes? Okay. Here's how to do it. There is no wait-free. There is no atomic max hardware instruction. You do it with a CAS loop. Same thing. You read it. If it's greater than the current, you try to atomically swap current with n. If nobody changed current, you succeed on that and you're done. If somebody did change current, you have to check again. Maybe they bumped it even higher. If not, you have to try again. Okay, let's look at the performance. There are two cases with very distinct cases with maximum. One is frequent updates where your current values keep increasing, so you keep updating maximum all the time. And the other one, infrequent updates, where you hit the lifetime maximum and then you almost never increment it. Okay, so rare updates, compare and swap. The fastest. Same rare updates, spin locks. It's right there, like this guy here. So it's hidden behind this line. Frequent updates. Okay, frequent updates basically are almost the same except at large number of threads. But for rare updates, spinlock doesn't take advantage of rare updates, and compare and swap does. Well, why? Well, that's obvious, right? The comparison is not involving this compare and swap at all. But every comparison is done under the lock. So if you never update, you would never do compare exchange at all, but you would still take lock every time. Well, it's not that the locks themselves are bad, it's that we're using them wrong. So here is another way, and the way I wrote it is typical way of using locks. To get to this style of writing, you actually have to kind of think of how would you write it lock-free, and then not write it lock-free. But this is, but then you arrive to this. So, okay, here's my log that guards the variable, and the variable is atomic. So, yep, I have both the log and the atomic. I'm going to read it atomically and do the comparison. And if I don't need to update, that's it, I'm done. Just like I didn't need to do compare and swap in this scenario, I'm not going to take a lock in this scenario. It doesn't matter how expensive the thing I'm not going to do is. Now, if I do need to do the update, then I have to take the lock. I may be wrong about it still being greater than max because somebody might have bumped max even higher. So I have to recheck that, and if I still hold the highest historic value, then I write it in. That's called double check locking. Yeah.
Why is it okay to do the relaxed mode in the seconded?
Well, the mutex itself has acquire release barrier semantics so gives you the barriers. But it's not okay to write this without release because there is a channel, there is a code path that acquires and never hits the lock. So well, I'm sorry. In this case, I wasn't interested in any other memory, so I said everything is relaxed. But if I was using that max to do anything else with it at all, other than just let's print it and forget it, I would need acquire and release semantics. Sorry. Yeah. In this case, I was just okay. Let's just count to max, and that's we're not going to use it at all. I'll just print it at the end, and that's it. But if I was going to use it for anything, I would need acquire release semantics on it.
Or you could take the spin lock again at the end.
Well, I could take the spin lock for the barrier effect. Yeah. Okay, so now let's see how quick this is. Okay, here is the rare updates. Again, it doesn't matter how expensive the thing that you don't do is. Rare updates take exactly the same time. Okay, now we have, what about frequent updates? And turns out that spinlock wins on frequent updates over compare and swap, because frequent updates means high contention. At high contention, spinlocks win. Okay, so here is your lock-free style programming, but done with locks. The idea is that you minimize the critical section to protect only the modifications of the state, and usually it's done by making some of the lock-guarded variables also atomic, so the non-modifying read-only path can be done purely atomically without hitting the lock. And the modifying path is the one that hits the lock. Okay, so now there's this kind of carves out some niche domains for lock-free algorithms where they excel, even though at high contention spin locks are faster. Okay, fine. So first of all, this is the traditional view. Well, log-free code is hard to write. You must use log-free code for the most critical code in your program, and the most critical code is highest contention, frequent updates to shared data. 2 out of those 3 things appear to be wrong today. You can guess which 2. The first one is still right. Okay, there is a niche when most of the data is read-only, so RCU protocols falls into that niche, for example. But our log-free style programming also competes in that same domain because it uses logs only to protect data modification, and the read-only path is log-free. When you can use cheaper memory barriers than what the logs provide, again, like RCU relies on just acquire and release only when you need. But logs, in effect, provide a full barrier because there is acquire at the beginning, there is release at the end. After you go through the entire log, you basically have a bidirectional barrier. If you don't need a full bidirectional barrier in the program, so RCU never needs bidirectional barrier. So maybe there is some room to play there where you can make your log-free programs still performance competitive because you can use cheaper barriers with them. So, but these are all kind of various niches. Now there are still the problems with logs, all the ones about the deadlock, there is all of that, and there is then the fact that the high contention logs are expensive, and unfortunately, the high contention log-free is even more expensive. And then, if you actually try to write this in a real system, you run into another factor that we didn't benchmark so far. You might have come up, I don't know, anybody here encountered the situation where you have some log-free data structure and you benchmark it and you actually manage to beat the spinlock or the mutex. And then you put it in the full program and the full program actually runs slower. Happened? Yeah. Okay, happened to me too. Okay, what we're missing is fundamentally, basically, well, in most general terms, interaction with other threads. But kind of more specifically, our log-based or log-free code, our high contention code, takes away resources from other threads doing other work. So that's a new factor to consider, the overhead of whatever synchronization schema we're using on other threads doing other stuff. Because real programs typically access shared data sort of in service of doing some other work. You have the queue, which has high contention on the like the task queue has contention on the entry, but the point isn't to actually cycle the queue. The point is for the tasks that come out to get executed. So we can try to model that, and so I've tried several different ways, and this is the one that I'll be using for all the benchmarks that I'll show in this act. So I have, on all my threads, I have some amount of shared work. So I'll be incrementing a shared variable. This x is atomic variable. So this is some amount of shared work. And then I have some amount of thread local, of non-shared work, and this is just some computations. And I'll change the ratio of the shared work to not shared work. And then I can do exact same thing. Instead of fetch add, I can use compare and swap, or I can use a spinlock. I'm not going to show the code because it's exactly what the same thing we were doing before for the shared. So I'll just do atomic, well, thread safe increment in 3 possible ways: weight-free, log-free, and log-based. And I'll vary the ratio of shared work and non-shared work, and we'll see what what wins. Okay, so that's our third act, where something is going to get killed, and there is a chance that it would be me. So here is that result, and the way I'm showing it, so I'll explain what's shown here, it's the performance, so it's a throughput, relative to that of the atomic. So I'm using fetch-add for my shared work. So I'm using fetch-add for my shared work, and whatever number I get from this, I call 1. I'll stick the spinlock instead, and I'll measure the ratio of that. So what this models again is the situation where, okay, I have to do this. The non-shared work is the work. This is my payload. This is basically what makes money. This is what I want actually to do. The shared work is necessary just in service. I need to do that in order to schedule these computations, in order to store the data in the shared data structure. Whatever I'm doing, this models my data sharing protocol somehow. I have to do that part, but I can choose how to do it. I can do it with atomic, or I can do it with a CAS, or I can do it with a spinlock. So the question is, am I better off doing it with a spinlock or with atomic? I can't not do it. But I have a choice of how to do it. So that's what this graph shows. Okay, and parallel to shared ratio. So 100 iterations of sharing for 1 iteration of parallel, not shared work. Maximum contention. I'm pretty much spending all of my time contending for shared variables. It's the opposite case. I have 100 iterations of math, which are completely local. All the variables are local to each thread. And then 1 iteration of shared data, of updating the shared count, and 100 more iterations of math. And look at that. At high contention, no surprise here. So just look at the shaded portion. Mutex is bad. We knew that, no surprise. So let's just do spinlock versus atomic. Okay. At high contention, spinlock is like 2.5 times faster than atomic. So one second. Using the spinlock to implement your data sharing at high contention is better. You get 2.5 times higher overall throughput. Now here your question is.
Can you go back to the last slide, please?
This?
No,
This?
Yeah.
Yeah.
So they are happening back to back, right? So what happens, even if I know the second one is not shared, nothing is shared, but the first one is shared, right? So depending on the first one, the second one will also suffer the first sharing, right?
No, it's different. Everything in the second one is thread local variables. Well, so there's your stack variables. There is.
So what if the variables end up falling in the same cache?
Nobody allocates. There are 2 megabyte stacks or 10 megabyte stacks. See, these are the y and the n word. The y and the I are your local variables. They're just on the stack in that function. Nobody allocates stacks that close.
Okay, so it's very
There are like 10 megabyte stacks per thread. So no, there is no sharing between your stack. There are variables in your function. So this is a function. There is somewhere at the top. There is, double y equals 0.
So the first portion is only the multi-threaded part. The second part is.
The second part is
This whole thing runs on each thread, but X is a single atomic that is shared between all threads. It's global. Y is a local stack variable in each thread. So the parallel work really is fully parallel. There is absolutely no data sharing in that parallel portion of the computation. Yeah.
Did you verify that the compiler didn't unroll your loop a bit and move your stuff?
It could reorder it, but in the benchmark I did put all these, do not
optimize.
Yeah, don't optimize. So reordering is possible, but I actually, don't really care. Don't optimize calls. So the 100 iterations of nested sign cosine have to happen.
Yeah.
It could rearrange the order, but do not optimize and global memory are inserted after every one of these.
I was actually worried about stamping out 2 or 3 copies of the outer loop and then coalescing.
So
one way or
do
the
not
other.
optimize is preventing that.
Okay.
Okay, so high contention, but we already knew that. There's nothing new here. We already knew about this. Spinlock is faster. What's interesting is this end, low contention. So very infrequently, one out of 100 times, I'm going to hit a shared data with either a fetch add or a spinlock. And if this is the speed of atomic, that over there is the speed of the spinlock. So this is this weird situation where it contradicts what I told you before. The work that you don't do, it doesn't matter how expensive it is. Well, here is the work that you almost never do, and yet it appears to matter how expensive it is. Okay, is that an x86? Okay, is that sorry, this is actually the ARM. So the label is wrong. I copy pasted the label. It's not an x86 thing. This is the Grace. So ARM-based server. Not an x86 thing. The logs are more. So ARM-based machine logs are even at high contention logs are even better, but at low contention, same thing. At low contention, the spin log that you very rarely take appears to degrade the performance of the overall system. Now, of course, if you keep increasing this ratio, 1,000, it's actually 1,000, it's still, spin log is still worse. You go to like 10,000, 100,000, at this point, like it basically never happens. Yeah, you will get, everything will run at the same speed. But at 1,000, you can still see that spin log is worse. 100 seems like, 100, and it's like, look at this. I mean, this is, it's 100 of these. They're fairly expensive calculations. And it's one of these, which is actually very cheap. And even at that ratio, spin lock is worse than atomic. Yeah.
I'm sorry, two questions. One, so
I saw it. Yeah. Go ahead.
Is that are you saying that there's like somewhere between 5 to 20% speed up in your full program at 100? Is that, I mean, if I'm reading that correct? Like,
yeah, there is. Well, no, it's like.
Is this? Let me ask this question. Did you calculate the time it takes for these shared operations to run against each other, or did you calculate the full time?
Yeah, this is just the full time. I set it up to do certain number of operations. Well, actually, I set it up to run for a certain. I actually set it up to run for like 5 seconds and count how many of these math. The useful work is the math. Okay. All these atomic increments are basically synchronization I have to do. They model like the task queue or whatever synchronization I have to do in order for my concurrency to work. So I set it up to run for 5 seconds, and how many of these math calculations I ended up doing. That's the throughput.
And then my second question was, it says atomic, but that was a weight-free.
Atomic is a weight-free, yes.
Yeah, but did you try it with something a little more, what's the word? Intense, like a pair exchange or something like that?
I tried it with the CAS loop too. Basically CAS loop is obviously at high contention CAS is even worse. I'm sorry. This is the CAS loop. Sorry, this is log free. Okay, it says up there log free. This one is okay. I'm sorry. This is weight free. This is log free. This answers your question. This is log free. This is the CAS loop. Yeah. So this is the CAS loop. Of course, CAS loop is much slower at high contention. We already knew that. It's worse than fetch add, even worse than spin lock. This is the interesting part. The gap is not as large. The gap here is not as large. So see, this was the gap at ratio of 10. See how big it is. This is the gap at ratio of 10 with the CAS. It's not that big.
The scouts changed the graph, right? So
well, I mean, we're below 1. So like this is about 40%.
And then the other one is.
And this one is about like 5x-ish. Yeah. Okay. So this is CAS is also better. CAS is more expensive than fetch add overall, but at low contention, In the low contention mode, CAS is better. You had a question?
It's answered.
Okay. All right. High contention, okay, we know everything about high contention. Dominated by high coherency protocol, the messy traffic, rapid back off, yeah, we know all of that, so we know why spinlock is better. So no surprise here. The weird thing is, at low contention, spinlock appears to be slower. Now, if you look at, for example, this data point here, spinlock is executed on 1 out of 100 iterations. And this is what, like 4 times slower, something like this. There's no way spinlock is that slow that being executed 1 time out of 100 iterations, it drags down the entire performance by 4x. Spinlock isn't the fastest thing, but it's not that slow, especially uncontended spinlocks. So what's going on? What's going on is spinlocks somehow degrade the overall performance of the surrounding code. But how? And now we have to go to the profilers. So you can, I did most of this on Intel because better profilers, but I've also tried it on ARM Zen. It's harder to get the right registers there, but I got them. I did a little bit of it on ARM. I'll show you what's specific for ARM is. There are fewer of the hardware performance counters on ARM. So this is what you can do it with VTune. You can do it with perf on it if you're doing Intel. Profiling with hardware counts. So is it branch misprediction? Well, spinlock and CAS both have branches in them, but at essentially 100 iterations of pure math, unconditional, and only 1 spinlock, branch misprediction shouldn't be that bad. And yeah, branch misprediction counts show that it's pretty low. Not that. Okay, is it stalls, backend stalls? Okay, let's get the backend stall count. On Intel, it's this cycle activity stalls total count. If you're using perf, many perf systems don't have that name, but this is the address on Intel. You can get it by address. Okay, atomic increment. I mean, the absolute number, of course, depends on how long you run this program. So absolute numbers don't matter. It's the ratio that matters. It counts over the lifetime of that entire program. The longer you run it, the bigger these numbers will be. The ratio that matters. Okay, 60 billion stalls with atomic increment, 60, a little bit more with CAS, but basically the same. Twice as many with spinlocks. Okay, that's interesting. Spinlocks, which happen only 1 time out of 100, are causing backend stalls. Now, backend stall is an aggregate metric of all backend stalls. It doesn't tell you why. It tells you specifically backend non-memory stalls. Backend stalls also include waiting for memory. The counts are different. This count tells you that it's the backend, but not waiting for memory. Front end, by the way, would be things like instruction decoding. Okay, there are multiple counts that go into the backend stall, and now that we know that we want backend stalls, we can dig into those. If you dig through them, you'll eventually find these two. There is a resource stall store buffer. That tells you how many times you stalled because store buffer was full. What's the store buffer is used for? Every time you execute a write operation on the CPU, it doesn't go into L1 cache like the textbook cartoonish picture says. It goes first into the store buffer, and from there it eventually makes its way to L1 cache. If the store buffer is full, CPU stalls because you can't execute writes anymore. Okay, here is our store buffer. Atomic increments never stalls. CAS never stalls. Spinlock. Yeah. There is another one, which is reorder buffer stalls. Reorder buffer is the instruction buffer. So all of our instructions that get executed are put in the reorder buffer, and then they come in the program order. Execution units reach out and grab them basically in random order as long as the dependencies are met. If the dependencies are met, any one of them can go. And then they get retired, again in program order. Okay? Reorder buffer stalls are actually higher for atomics, lower for spinlocks. Okay, that's weird. Okay, so that's not obvious, but the store buffer stalls, that's the real culprit. And now we come to this key difference between synchronization provided by locks versus synchronization provided by atomics. So in both cases, we're incrementing an integer. Integer itself could be atomic, and then it's its own synchronization. Or it's guarded by a spinlock, and then another variable, the spinlock integer flag, is used to provide synchronization implicitly. There is no connection between the guarded counter and the spinlock, except for the ordering guarantees. So now we have to talk differently about x86 and ARM. So x86 only for now. Exchange is a full memory fence, which means the load store unit, and exchange is what sits inside the spinlock. Load store unit has to halt and wait for the store buffer to drain. That's your store buffer stalls. CAS and atomic operate on a single shared variable, so effectively you fuse control and data into the same variable. So the implicit execution dependency turns out to be bad for concurrency.
No.
Now, the interesting thing is that spinlock is actually limited by store buffers and not instruction retirement. Why? Because the reorder buffer stalls actually dropped with the spinlock. Why wasn't it bad? I mean, why wasn't it good? Sorry, it's not a good thing. It turns out that that's actually not a good thing. Why? Because reorder buffer typically stalls when the CPU executes instructions so fast that the reorder buffer fills up, and it has to wait for somebody to retire. You want that to happen. That's what happens when you shove in pure math into the CPU. The spinlock forces the store buffer stalls, so reorder buffer doesn't fill up as often. So the fact that a reorder buffer stalls, there are more of them with atomic, is actually shows you that it executes more code and stalls because it can't retire them fast enough, as opposed to it has to stall and not execute them. Okay, that's x86. On ARM, store buffer can commit to L1 in any order, not in retirement order. On x86, store buffer has to commit to the cache in the strict order of retirement of instructions. On ARM, any order you want. So, and yet, low contention regime on ARM also favors atomics. Why? There is still implicit data dependency, and the difference between the difference between the spinlock and the so on ARM, by the way, I didn't show that picture, but on ARM, fetch outperforms significantly better than concurrent swap at low contention. Concurrent swap still performs better than the lock. So there is this little trick on ARM that I'm going to show you. At very low contention, you always get the spinlock. I mean, the odds of you are actually colliding on that spinlock in low contention mode are practically like zero. There is a branch inside the spinlock, but it's 100% predictable. Almost 100% predictable. The branch you can measure the branch prediction, it's not a problem. Branch predictor is supposed to ensure that you don't pay the price for predicted branches. There is a dark side to speculative execution. I assume everybody knows what speculative execution is, right? Yeah, okay. So branch predictor assumes the outcome of a branch, such as a spinlock or concurrent swap, executes instruction in speculative context. If the predictions are accurate, it's almost as fast as unconditional code under normal conditions. Execution unit executes speculative out of order, but there is a catch. Instruction retirement still happens in program order, even on ARM. Store buffers drain in random order. Instruction retirement happens in program order. If you reach the instruction retirement point where you have to retire, and you're still in speculative context, you can't retire. At that point, you have a stall on the reorder buffer, and you have to wait. So that's one case where speculative execution is slower. Perfectly predicted speculative execution is slower than branchless. Normally it doesn't affect you. Normally it never happens. The reorder buffers are designed to be long enough that it doesn't happen. Except these contended, the concurrent swaps and atomic exchanges are long enough latency instructions that it does happen. And there is a counter on ARM stall backend that measures that. Okay, how much time do we have?
35.
Okay, great. So now we have all this nice picture. We know that at low contention we want to use atomics and at high contention we want to use spin locks. Let's use this knowledge to build some data structure. And of course the data structure we're going to build is, anyone?
Q.
Yeah. Multi-producer, multi-consumer queue. Not going to be lock-free, but okay. So here's our new wisdom. Use lock-free, of course, when other lock-related issues are important, but use it at kind of medium contention. That's not something we do normally. We typically say at low contention, it doesn't matter what you use the easiest. So what we're going to do is we're going to use the spin locks at high contention. We're going to use atomics at low contention. We're going to minimize the critical section the way we've seen before with this atomic handoff from the critical section. We're going to write this multi-producer, multi-consumer queue. All the standard stuff, power of 2 size ring buffer with head and tail. One detail of this one, for the keys, I'm going to require that one value can be reserved. So let's say, for example, if the queue traffics in pointers, null pointer is special. So you can't send a null pointer through the queue. Null pointer value is reserved for the queue. The way we're going to put it together is like this. So here's our ring buffer. We have the head index. We have the tail index. And we have these slots, and inside the slots you have the atomic key. You have this additional busy value, and you can have the value. Ignore the busy value for now. It's very special case. What are head and tail? Head and tail are actually two separate domains. They're both high contention. Producers, the ones who push, contend on the tail. Consumers contend on the head. They're both high contention. They're both going to be spin locked. Now, they're also going to be on separate cache lines. There is absolutely no reason for producers and consumers, at least, to fight each other. Okay. And then we're going to, basically, as soon as we're done manipulating the tail or the head, we're going to release the spin lock. Because at that point, we grabbed our unique exclusive slot. Now, the contention for the slot is low. A unique exclusive slot, other producers don't contend for that slot. Another consumer could possibly contend for that slot if they happen to coincide. But in general, contention for the slots, for each individual slot is low. That's where atomics come in. So on the slots in the low contention mode, we were going to use that atomic key to synchronize. On the tail and head indices, in the high contention mode, we're going to use the spin locks to synchronize. That's basically the push. Acquire the tail lock, check the key, ignore the busy. Increment the tail, release the spin lock, then construct the value in that slot. The only reason we actually have to have the busy is there is I have a slide. There is this exotic data race with a producer wraparound, where one of the producers runs so far ahead of the other, it circles the entire ring buffer, comes back and tries to fight for the same slot. And for that you need that busy flag to tells you no, somebody else is constructing the value in it. Okay, so this is the contention profile. This is what it looks like. On the pushes, we have these spin locks, they have to be staggered. On the pops, the spin locks, they would be staggered between the pops, but they're not contending with the pushes. And after that, we have this atomic stuff happening. Now, constructing the value isn't atomic at all, but the key store is the atomic that guards, signaling the key store, and if you have busy, the busy store is what signals that slot is done.
Sorry, could you go back to what that key is again? I missed that, I think.
The key is in every slot.
Okay.
So setting the key from the reserved value to non-reserved value is what signals that the slot is constructed.
I see. You're not using like you're good to read to this point because
Well, key is a reserved. I'll get key is a reserved value. So if you didn't have the wraparound, let's forget about the wraparound.
Yeah.
If you didn't have the wraparound, then you would just say, okay, as a producer, I have exclusive access to this slot. I can construct the value at my leisure. Consumers would come and look at the key. Let's say the keys are pointers. See 0 and wait.
I get it. Sorry, my brain was in single producer mode where I didn't understand why there wasn't just a variable that says now the consumer can consume up to this point, but they obviously that.
Yeah. So I finished constructing my value. Now I atomically update the key. Now the consumer sees that okay, that slot is finished constructing.
Yeah.
Okay, yeah. See that? Okay. You had a question.
Yeah, why are busy and key separate atomics? Why are you not bit
Yeah.
Okay, that's the yeah. See that that's the wraparound possibility.
Sure, but why are you not bit packing them into the same atomic so you can hit them both with the same pass?
Okay, so you could do that. It depends on the size of the key. So I wanted to allow the pointers as keys, and I didn't want the double cas.
Right. Okay. Because I mean, you could pack it into the lower bit because you just need.
Yeah, then I would have to do bit manipulations, and you can do that, but and I mean, in some cases maybe it's faster, but you would have to do bit manipulations. Okay, yeah, question.
Well, why do you need the key? Would the busy atomic not be enough? Like, why do you need the key to be?
Because well, in the key, first of all, in the key only mode, I actually don't need the busy. So I'm showing the generic case with the value. In the key only mode, I don't need the busy. Key is what communicates between producers and consumers. Busy is just for that wraparound case. Okay, a wraparound case. All right, let's see some data. Okay, the list of other queues I pulled, whatever I could download and conform to the benchmarks that that I have written. Throughput. So there are two modes for the keys: high throughput for the queue. Sorry, high throughput and a low latency. High throughput is basically you're shoving a lot of stuff into the queue. Queue tends to be mostly full-ish, and what you measure is the just you basically you run it for like 5 seconds. How many millions of things pass through the queue? That's the throughput mode. So okay, Intel Granite Rapids. As a function of number of threads, logarithmic scale. Logarithmic scale. The 4 ones on the left are all are the 4 variants of the queue that I've shown you. There are variations, and basically how do you align the slots? You can have just the slots unaligned at all. That's 0. You can align each slot on a cache line. If all you have is 8-byte pointer keys, you're wasting a lot of memory in doing that. You can align them on 128. Now, some of these other queues actually have aligned slots, and some don't. So for my queue, I can vary it. Okay, at 2 threads, there are, the higher the better. At 2 threads, there is one queue that is effectively kind of a single producer, single consumer queue with safety for MPMC. It does the best for just 2 threads. 2 threads, one producer, one consumer. At large number of threads, it outperforms everybody else. Now, benchmarks, a lot depends on how you set up benchmarks. So, my benchmarks on GitHub, you can try your own. One of the things I did, not for throughput but for latency, I've actually taken a benchmark out of the suite of one of those queues and used their benchmark, and you'll see the results of that for latency. Okay, that was log scale. This is what it looks like in linear scale. So this is Granite Rapids. AMD Zen 5. Different timings on this machine. It performs pretty well. Okay, let's skip this. Grace. Everybody collapses in grace for very large, for maximum number of threads. They have basically cache domains so that you really, if you on this processor, if you want to have a queue and you want to use all of its cores, you basically do the same thing they do on NUMA, set up multiple queues per node, and there are balance between them. M3 Pro. Okay, what about latency? On latency, I have a problem. My queue is log-based. I should be slower on the tail latency. Well, the only question is where the tail is. Okay, let's start with average latency. Average latency, this time the lower the better, again log scale. Lower the better. Average latency is related to throughput, so no surprise here. %95 latency. Pulling in closer. 99. The gap is closing. 99.9. Okay, now at that tail, some of the log-free queues can beat mine. Not unexpected, they should. The only question, yes, log-free queue in the very tail of latency will outperform log-based queue because preemption is real. There are two questions: where, and how much are you paying for it in the average case? Where? Well, here. How much are you paying for it? In the average case, this much. Now, depending on your application, this actually may be acceptable price. I'm not saying that, look how much better it is. These are the factors. For your application, all of this may be irrelevant and this may be critical, in which case you can't use log-based queues. Finally, latency, giving you 95 and 50% and all that is fine. I wanted to show the full histogram. This is a density curve of the latencies. So percentage, latency in nanoseconds. This is that spin-lock atomic hybrid. Obviously you can't see the tail, the values are too small, but in the tail, eventually, some of these log-free queues will win, always win. You just have to get far enough into the tail. Okay, ARM. Okay, as I said, you can't see the tails. So, pictures versus 1,000 words. Some pictures still need a few words. So, I picked one of these queues from the previous chart, and I'm going to actually show you, what the actual numbers are. Okay, at 50%. Well, this is actually this machine, but it doesn't matter. So at 50%, that's somewhere near the peak. My peak is at 320 nanoseconds. That other queue peaks at 82,000 nanoseconds. At 99.9%, they're about tied. At maximum, they have much better guarantee of a bounded maximum than I do. Yes?
So when we're measuring latency, what time are we actually looking at?
Okay, how do I measure latency?
Is it push to pop?
Okay, latency is measured. There are two ways that I measured latency. So first of all, the timer itself is our DTSC count. One way is the queue is being intentionally run almost empty. Because latency on the full queue just depends on how much stuff you put in the queue and how big your capacity is. You make a queue of size 10 million and you keep it full, latency will be a minute.
Yeah.
So I keep the queue almost empty, and yeah, it's a push to pull. The other way to measure latency is a ping pong test, where you have two of these. It's limited to like 2 threads or however many threads you set up to ping pong. So that was push to pull. On the queue that is intentionally kept near empty.
Yeah, I just wanted to know what I'm actually looking at.
Yes, you're looking. So it captures our DTSC, which is also 8-byte value, uses it as a key, no value, pushes it into queue. As soon as it pops, it captures another DTSC, looks at what it just popped, takes the difference, plots the density curve of those values.
Yeah, good. Thank you.
Okay, it's always possible that I screwed up somewhere, and that's why I'm here showing this to you. If I didn't, the conclusions appear to be that the design based on spin locks at high contention, lock free at low contention, and minimizing the critical section using this combined, like using locks only for writing and on as tight a critical section as possible, appears to work and give you better performance, except preemption is real, and if you need tail latency, anything lock-based can be preempted and sometimes will be, and there's nothing I can do about it. The question is where and how often. I've tested on multiple x86 servers, Intel and AMD, several ARM servers. I've tested on my desktop. I've tested on my laptop. Overall, it holds. Like the ratios are different, the values are different, the qualitative are the same. So even with all of that, I mean, I'm afraid that I made a mistake. I'm also afraid that I didn't. Because if I didn't, we have to write our low contention path that we never cared about differently. Okay, I had a question.
Yeah, so just understanding that one. So you have a table, and you don't have something like capacity to understand how much data is there. Then I mentioned the benchmark, you always try to keep it empty. That means head and tail belongs to the same pointer. So if that is true, then all the producer and all the consumer trades, they're all happening at the same.
They're close. I mean, like, see, if you keep it completely empty, then what you're measuring is not the queue latency, but how long you wait on an empty, how long your benchmark set up to wait on an empty queue. You don't want to do that. So it's not like, you know, if it always changes between 0 and 1, then what you're measuring is, if you want to see that how like shifting between 0 and 1, you have to set up the ping pong test, because there you can actually control it. So it's near empty, but it's not empty in this benchmark. If you actually want 0 and 1, you set up the ping pong test.
One more follow-up question.
Yeah.
So when you have wraparounds, right? So your tail ends up going to the end, then came back.
Yep.
So you want to know that your wraparound, so that you don't override. How do you make sure? For that, you need to know that your head is more than tail. So for that also you need both of the data, right? How are you making sure you don't need both of the data?
The consumers can progress beyond tail. They just won't be. They'll just know that the slots aren't ready.
Consumer can produce.
Consumer can progress their index beyond what producer produced. It's just the slots will be marked as empty.
So they'll just keep trying empty slots and be like, oh, nothing is there, nothing is there.
Well, no, they only try their slot.
Okay, so let me just ask the question and reframe the question. So suppose the wraparound happened and the queue ended up becoming empty. How do you know that from consumer point of view?
The consumer wraparound.
Yeah.
For consumer, it doesn't matter. I mean, they will be both contending for the same slot. One of them will drop the key from non-zero to 0, and that one gets it. That's still atomic. The other one doesn't. Okay, so the traditional high contention domain for lock-free programming appears to be dead, with the exception of some niche situations, and especially if you do this minimization of the critical section by combining locks and atomics. The overhead of log-based synchronization in a low contention regime where the cost of log itself is irrelevant, but the disruption it does to the execution pipeline of the CPU, that seems to be real. All the profilers on Intel, on AMD, and on ARM confirm that for slightly different reasons, but that disruption is real and it causes backend stalls. And it's caused by this implicit. The fact that the synchronization schema with the lock is implicit to two different variables that have to be mutually ordered. Basically, the CPU cannot reason through that implicit dependency. So it decides, okay, I cannot figure out how to predict through that, I'm gonna just flush everything, wait until the situation resolved itself, until the conditionals are met, whatever they are, and restart the pipeline. The ARM and x86 do it in slightly different ways.
So do you know what mechanism is actually going on? Because I mean, I have a reasonable understanding, I think, of how the store buffer is involved in like a compare exchange, the spinlock loop, with the flush that you're talking about, and waiting for the store buffer to drain, and obviously you can't get any loads beyond that and that. But you kind of waved your hands a lot and said it's optimized for an atomic increment, and I don't know how that process works. I don't know what manifestation.
Well, okay, see, with atomic increment, it doesn't have to do that. There is no global barrier that, unless you do atomic increment unless you follow atomic increment with like LFENS, which you would do if you put SexAST on it. But unless you follow it with LFENS,
I don't even know that compilers will generate an LFENS under any circumstances for x86.
For x86, maybe not. For ARM, they would have to.
Right, so but that's why I'm surprised by this. I'm trying to work out what mechanism that makes that better, like at the hardware level, what the atomic increment is doing that is different from essentially a load of the store.
Atomic increment is just an instruction. So in this sense, it has a data dependency, but CPU knows about that instruction as much as it knows about any other data dependency. It's in the spinlock and the guarded variable, there is no data dependency between them. It's not like one of them is pointer to the other.
Mm-hmm.
CPU cannot see that there is a dependency. So, but there is one, and it's not expressed in the memory barriers create the dependency, right? You have to wait until you see the log become until you are the one changing log from 0 to 1, and only then you can increment your integer. So there is a dependency, but it's not a data dependency.
Mm-hmm.
It's not like the CPUs know how to analyze data dependencies, like pointers to values, indices to offsets to memory. They know how to deal with that. But there is basically nothing, as far as I know, in their analysis of the incoming instructions that allows them to do any reasoning on this implicit dependency created by the barrier, by the fact that when this is 1, this can be modified, even though it's not a pointer. So if you point to something, so when the pointer points, I can read it. They know how to order these instructions. They'll just order these two without messing with anything else. All the other instructions will flow around that. These two will be ordered.
I think probably I've probably derailed you too much. We could perhaps talk about this offline.
Let's talk about it offline. Okay.
Thank you.
Yeah.
So one quick question. Just wanted to make sure. What memory order was used to implement the spinlock? Was this
Spinlock always has the same memory order: acquire and release.
okay? Just one.
That's all. That's the minimum you need. Okay, of course, atomic exchange on x86 gives you the full barrier. It's written with acquire.
Okay.
That's not what you get. On ARM, that is what you get. Okay, I promised you last minute surprise. I'm going to show you, and I didn't come to the lightning talk. Okay, so these are like 4 things that I discovered while preparing this talk, and I didn't have time to prepare a material for them, and I wouldn't have time to include it in the talk anyway. But the 4 things are: 1, when I was done like writing it and building the data structure, I looked and said, okay, wait a minute. If what I'm saying is true, you shouldn't put the spinlock and the guarded variable on the same cache line. Why? Because if somebody pre-reads the spinlock, they'll drop your exclusive to shared, and what you're trying to do is write into that damn integer, which is now sitting in the shared state, and you will have to issue a second RFO to get it back in exclusive. And there is no reason for it because there is actually no contention for the integer. You're the only one modifying it. You should own it, but you don't. So if I'm right, then the very common rule of putting spinlock and guarded, or the lock and guarded on the same cache line so you own the cache line is wrong. But everybody knows that this is true, therefore I cannot be right. And then I did this benchmark that I've shown you yesterday, and the benchmark shows that yes, it's faster to not put spinlock and the guarded on the same cache line. And yes, I think the reason is I didn't have time to profile it, but I think the reason is if somebody else tries to read the log, the log does the pre-read, so nobody's doing acquire, nobody's hitting it with atomic exchange. They're just reading it. But reading pulls everybody's cache line from exclusive, invalid, invalid, invalid to shared, 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 shared. And your integer sits on the same cache line, which means you need it back to modify it, which means it's a second RFO. If your integer is on a separate cache line, nobody cares about that, you'll get a cache miss. But at high contention, cache miss is cheaper than an RFO. At low contention, when RFO happens only rarely and cache miss happens every time, cache miss is more expensive. So yes, if you set up the same experiment, but the contention for the spin lock is actually very low, eventually it becomes better to put them on the same cache line.
But if by your presentation at that point, if you're at low contention, should you just use atomics?
Yeah, well, yes. But as far as if you're just measuring that benchmark of spin lock and atomic on the same cache line versus different, and you vary contention, there will be a crossover. Okay. Intel has the next line prefetch. Intel CPUs have 64-byte cache line, but they aggressively pull the adjacent cache line in when you touch one. It does appear in some of these benchmarks. I didn't have time to fully investigate it. AMD introduced what's called a near memory atomic in Zen 4. So everything I told you about this cache coherency protocol, what they did instead was, if you want to do a fetch add and you don't own the cache line, you send a request to the memory controller.
This is what I was kind of getting at. I was thinking something like this might be going on, so thank you. Yeah.
So on AMD, on Zen 4 and above, if you want fetch add and you don't own the cache line, instead of sending a request for sending an RFO for exclusive cache line ownership, you send a request into that same fabric. L3 memory controller, would you please do that? It has its own LU sitting on the memory controller itself. It does the increment. It invalidates everybody's cache lines now. So L3 is the only owner now. L2 and L1s are all set to I, invalid. If you wanted the result back, you get 8 bytes. No, you don't get the cache line in. You get 8 bytes sent to you by a packet through the same protocol. It is observable. It makes some of these benchmarks run around on the machines that have that look very weird. I said I didn't have time to work with that. I noticed that some of these benchmarks are like, wow, what's going on? Fetch add is like, now it doesn't work for CAS. CAS still requires a normal cache coherence. But okay. And one last thing. What if we inserted the aggressive backoff that saves our spin lock into the CAS loop? Again, I only had like one day to try it out. So, you know, I could be missing something, but in my very fast experiments, it did not make any difference or made a slight difference to the worse on all systems I tried, except for Apple Silicon, where at high contention, CAS loop outperformed fetch add and popped up to about half of the spin lock's throughput. Still not as good as a spin lock, but like 10x better than fetch add, and only losing to spin lock by about 50%. So it looks like now in a fetch add you don't have that option, but in CAS you do. People don't normally do that, but you can. And the reason people don't normally do that appears to be very good. It normally doesn't help, but on Apple Silicon it does. Again, the last minute surprise, I haven't had time to work with that. Okay, so 3 main points that I believe to be true, as to the best of my knowledge. Logs work better at high contention if you do them right, and doing them right means pre-reading with retries is critical, and you have to pre-read long enough for the RFOs to make your way back to you. Backoff is essential, and that's because the hidden cost of the log is in its release, and you don't want other cores to steal your exclusive cache line state. Log-based code can be made better by injecting atomics for read-only path through that code. And finally, for reasons that, to me at least, were totally unexpected, log-based code appears to poison surrounding code in low contention regime, not because the logs themselves are slower, they aren't that much slower, but because it just disrupts the overall execution of instructions in the CPU, and that poisoning seems to have kind of like a very kind of, it's a strong poison, very long life. So doing lock on 1 out of 100 iterations is enough to measurably poison the overall throughput of the CPU. Yes?
Can you go to the last slide, please? Yes, last point. So if you are using weak on an ARM system, the two different ARM, LSC ARM and LSC ARM. LSC ARM is better to use spurious areas like the failures, right? So you touch it, it fails, done. But if you are using LSC, then weak and strong works the same way, right?
Yes, on LSC, so weak CAS is kind of dying breed because, yeah, weak CAS exists only on ARM systems with LSC. Just like x86, the ARM CPUs that have a CAS instruction do not have that weak casting. By the way, if you do that back off, you have to use strong CAS, not weak CAS.
Yeah.
Yeah, forgot to mention that. If you want to try the back off, you have to use the strong CAS. Any other questions? Yes.
Why is the CAS emits the M fence? Right, that's what you said.
It doesn't have to. If you need a barrier bigger than CAS provides, you would have to emit.
But if you don't need, because you said
if you don't need, then it doesn't.
Because what I understood is in the low contention scenario, when you say the lock pollutes or
in the low contention scenario, CAS is doing pretty good.
Oh, sorry, I meant the exchange and swap.
It's not the barrier on the exchange itself. It's well, I mean, it is the barrier on the exchange itself, but it's the fact that the barrier sets up a condition, a dependence. So the barrier sets up this ordering between instructions. You have to CPU somehow has to guarantee that order, that the guarded variable is not modified outside of the critical section. But it's not expressed as a data dependency. Data dependencies, basically, we know how to handle them in hardware. So we know how to flow around them, essentially. The data dependency will order only what needs to be ordered. All the other code, we know how to flow around it. For this implicit dependency that's expressed by the barriers, as far as I can tell, there is no sort of way to flow other code around it. You have to. The only way they know how the CPUs know how to do it is to is to just halt the entire pipeline and execute these two instructions in order, and everything else that happens before would drain, and everything else that needs to happen after would wait. Because normally other code not related to this code path gets executed out of order. As far as I can tell, that out of order execution pipeline stalls.
So you're saying for the exchange operation, it stalls the pipeline, and for the CAS, it doesn't stall the pipeline?
CAS is so. So I see what you're getting at, and so the profiler clearly shows that it doesn't flush the store buffers. So this is a store buffer flush count. The profiler clearly shows that it does not flush the store buffers on CAS, and it doesn't flush them on atomic increments. So somehow it can figure out that this basically only depends on itself. There is no other instruction that needs to wait for this, because this modifies the data itself. So it can execute the CAS without. I don't think it's the instruction itself. I think it's the pair. It's the fact that spinlock has lock and unlock. Because you can do spinlock with the CAS and it wouldn't help you. It would actually make things worse. So it's the lock and unlock. It's the pair of the barriers. It's the existence of the critical section.
So you're suggesting that maybe the implementation of the spinlock makes more writes, and the more writes fills the store buffer. Therefore
No,
we have more.
spinlock eventually does one write when it acquires it.
And another
'Cause
write for the release.
well, okay, spinlock at high contention can do multiple writes because you can fail on exchange. But at low contention, you almost never fail on exchange.
So it does additional 2 writes for the acquire and the release.
But it does a second write for the release.
Mhm.
And the restrictions are bidirectional, right? The release also binds the critical section from below. Your integer increment has to stay between the atomic exchange, acquire, and the release store. So that appears to be the thing that causes the store buffer to stall. I don't know deep enough details of the architecture to say how they reason through this. They appear to be able to reason through this as long as basically control and synchronization are fused on the same variable and there is only one instruction that does the barrier. They clearly can't reason through this, through the 2 barrier synchronization where you have before, in the middle, and after. So acquisition, increment, release. That critical section basically causes the entire store. Before you enter the critical section, store buffer is drained. Nothing happens while you are in the critical section, and then it restarts.
There are no instructions for the spin lock. It's not like the x86 needs anything. There's no like draining instruction or
No. Spinlock, you've seen the code. Spinlock is read, exchange.
Yeah, the exchange is perhaps the one thing that's different.
Yeah,
Anyway, sorry.
but you could replace exchange with the CAS. I mean, you say CAS 01. It actually makes things worse. I mean, CAS is just slower than you're using CAS to implement atomic exchange. It doesn't make things better.
Do you have a question?
No, I think
Yeah, there was a question.
You mentioned on the branch prediction front that the dark side of it is that with the reorder buffer you can't retire instructions, and obviously that leads to more stalls. But like on x86 too, like I was also wondering about the store buffer, and like shouldn't there be an issue with there too? Because like when stuff is put into the store buffer, they're put in marked speculative,
Yes.
and they can't be, because x86, unlike ARM where it can flush in any order, x86 has to flush in the order that's put in, right?
x86 has to flush as in the order of retirement, yes.
In the order of retirement. But if that stuff still in the store buffer, it's marked speculative, then that should stall things too, no?
It probably does. It appears to be not measurable compared to this thing going on, the flushes of the store buffer. I'm sure it doesn't help, but you don't seem to be able to measure it. Like the speculation fails aren't that big.
Okay.
So the speculation, I've measured all the counts related to branch prediction, the failed speculation, the machine clears. It's not that bad.
But in your benchmarking, it is more bad for the reorder buffer in this case. Like if things. I'm just asking because you specifically brought it up.
Here's the reorder buffer.
Yeah.
Reorder buffer stalls a lot more on atomic increment and CAS because reorder buffer basically will stall if you're executing so much math that you can't retire it fast enough, and that's what's happening here.
Okay.
Spinlock.
Are you sure that is? Because modern Unix can retire like 6 instructions per cycle, which is an awful lot more than you can usually issue and complete. So I'd be very surprised if that's what it was measuring. It could be like, I can't write. Yeah, I don't know whether that means that the ROB could not retire anything at all, so therefore the ROB was on it. No, that would be a different thing again. I don't know. Yeah, sorry.
Okay, so the counts are what they are now. Why? Spinlock stalls a lot less often on row, but stalls on the store buffer. What the counts tell me is, so first of all, the counts tell me that actually the number of stalls is pretty significant. These are just now. Okay, so compared to the overall backend stalls, they're actually not that big of a fraction. So you're right, reorder buffer doesn't stall that often.
I mean, ultimately, whenever you measure anything, something is a bottleneck somewhere. So
Something is a bottleneck somewhere. Okay, so reorder buffer is the bottleneck only in about 10% of the cases to begin with. Yes. Within that, spinlock doesn't hit the reorder buffer bottleneck nearly as often as the other two. But yes, about 90% of the time, it's not this.
So if the weightage for both store buffer stall and reorder buffer stall, if the penalty for both of them are equal, then cache should be for.
I don't think it is equal.
So, do you have a number how much fraction penalty?
Well, see, this tells you how many stalls there were. I don't know of any way to know how long you waited on them. Because see, the store buffer on x86 is weird because I actually need to clarify something. So you don't exit the store buffer on x86 in the order in which it was written. You exit in the order in which instructions retire, which isn't necessarily the order in which stuff gets put into store buffer, because they execute it out of order, and whatever is executed gets put into the store buffer. So in whatever order they get executed, that's how it goes into the store buffer. But exiting the store buffer happens in retirement order. So you don't exit store buffer out of the tail. You exit it out of, you exit it in the order of retirement, but which means that if whatever is at the tail of the store buffer is not retired, even if the next thing is, the store buffer on x86 stalls. So because, on x86 you exit it out of the tail, but if it's not ready, if the thing that is currently at the head of the store buffer ready to exit isn't retired, nothing exits. Yeah.
For that one, was the data guarded for the spinlock on the same cache line, or did you try it with different ones for the low contention?
For this one, the spinlock was on the same cache line. This was before I had that thought that, oh damn, I'm contradicting something that is universally true. I must be wrong.
Do you think it would matter? You think it might change?
I did a very quick test of that queue by split, because I didn't do the benchmark, but it was easy to split the spinlock and the tail and the head in the queue. The results, and I did just one test, the results were inconclusive. It seems to be that at very high contention you can get about like 15% more throughput if you do that, but there are other regimes where you'll actually lose, so the results are inconclusive. For the pure benchmark of just doing atomic increment under spinlock, results are very conclusive. In the context of the queue, results were inconclusive. Well, if there are no more questions, then thank you.